Thank you very much for that introduction, and thanks for having me in your seminar. And I fully agree, informal seminars are good, so if you have any questions, please do interrupt. And the topic I will be talking about today is in part about Lagrangian multiforms, which is a variational principle for integrable systems that has been going for about 15 years now, so still very relatively recently. And in particular, I want to talk about my most recent work with Chenya Ferapontov, looking at some connections between Lagrangian multiforms and conservation laws, and in particular at some examples of dispersionless integrable systems. And the outline of, or the plan of my talk is more or less as follows. For the introduction, I will look at Lagrangian one-forms, which is the case that describes integrable ODEs. Though the main part of the talk will be about two forms and higher forms describe PDEs. And to make the link to conservation law, I'll revisit something that was done about 5 years ago, how to systematically construct these multiforms from variational symmetries in Noether's sense. And then we will extend this, in a sense, to more general conservation laws. And then as an additional example of dispersionless integrable systems from our paper, I will talk about hydrodynamic reductions, and in particular, the second heavenly equations. So let's start, as I said, with Lagrangian one-forms. And the situation they describe is essentially that of a Liouville integrable system. And so to start from the same place, let's just imagine a Liouville integrable system, which is a Hamiltonian system on some symplectic manifold. For simplicity, let's just assume it's a cotangent bundle. And so it's Liouville integrable if it's part of a family of n Hamilton functions such that the Poisson bracket between all of them vanishes. And this has a lot of very nice properties, as many people will know. In particular, relevant to our purposes is that there's nothing special about the original Hamiltonian H1 here. In the definition, all of the H1, H2, Hn are interchangeable. So each of these Hamilton functions could define its own flow, its own dynamical systems. And each of these, because the Poisson brackets vanish, each of these n Hamiltonians are conserved quantities of all the n flows. So this combined dynamics stays on a common level set of these H's, which, as the famous Liouville-Renaud theorem, is a torus. But the most important detail in here for us is that these flows commute with each other. So we can think of a solution to this dynamical system, not just as one flow depending on a real time variable, but as n flows, so as a function of n time variables. And so, for example, if we draw the picture with 2 times, we put some initial condition for both times equal to 0. And then by the fact that the flows commute, it doesn't matter how we get to a different point in this multi-time plane, the state there will be well defined. So we can think of solutions not just as a function of a real time variable, but as functions of multi-time. And this multi-time is the setting where Lagrangian multiforms are defined. So suppose we're still in this Liouville integrable situation, and so we have a number of Hamiltonians, and suppose that somehow we can do a type of Legendre transform and get to each Hamiltonian Hi a Lagrange function Li. And to get to Lagrangian multiforms, the first step is what is sometimes called pluri-Lagrangian principle. And the terminology here is sometimes a little confusing. because the difference in the concepts is quite small. The difference in the name is in part geography. Pluri-Lagrangian is the name that Yuri Zuris and his group in Berlin likes for this kind of thing. Lagrangian multiform is the name that the group in Leeds, started by Frank Nijhoff, prefers. And they have slightly different perspectives, hence that we can attach these names to different things. So the pluri-Lagrangian principle, we take these Lagrange functions Li and we combine them into a one form. A one form that lives in this multi-time. So we just take Li dti sum over all time variables, and that's our one form. That's the central object in pluri-Lagrangian principle or Lagrangian multiform theory. And the pluri-Lagrangian principle then says, well, it's a one form, so we can integrate it over any curve in this multi-time. Over any gamma, we can take the integral. And no matter which gamma we choose, if we take variations of q, of the dynamical variable, then these infinitesimal variations of the action should vanish, no matter which curve we choose. And this is stronger than just requiring the usual variational principle for each Li, because say we choose the horizontal line as our curve gamma, then the integral will only see the dti components, so the action will just be L1 dt1, which is the usual action for L1. Same if we take a vertical line, we would get the usual action for L2. But obviously there are many more lines than just horizontal and vertical. We can, and these will have different actions that also need to be critical. So this is a stronger principle than just the individual Lagrangians combined. And if we're really doing Lagrangian multiform theory, there's usually an additional requirement. So we require the pluri-Lagrangian principle, but we also require that on solutions, this one form is closed. So geometrically, that means if we take a small perturbation of our curve, then this will not change the action. Because by Stokes' theorem, the difference between those integrals will be the integral of dl over the region in between, so that will be zero. So the Lagrangian multiform principle is, in a sense, two different variational principles about the same action. One is the pluri-Lagrangian one, that you take variations of q and you should have a critical action. The other one is taking variations of the curve gamma that defines the action. Now, if you define a variational principle, what you want to ask is, well, what are the Euler-Lagrange equations that characterize it? And for simplicity of presentation, I'm going to make here a quite strict assumption. So in general, I write square brackets of Q indicating dependence on an arbitrary jet bundle, so arbitrary high derivatives. But for the sake of the next few slides, I'm going to assume that L1 only depends on Q and its T1 derivative. Subscripts are derivatives here. And for I different than 1, I'm being slightly more generous. I'm allowing the Ti derivative, so corresponding to the index I, but also always the T1 derivative is allowed in the Lagrangian. The reason why I do it this way here is that the simplest examples that we know of are of this form. So this is as restrictive as I can really make my assumptions without becoming trivial. So I consider the one form made out of the, components with this dependence on derivative. And then the multi-time Euler-Lagrange equations, or also multiform Euler-Lagrange equations, they are the equations that characterize the pluri-Lagrangian principle. So the equations that make sure variations with respect to Q are critical for all these different actions. And they come in more or less 3 types in this case. The first one are the usual Euler-Lagrange equations for each Li. We take the usual Euler-Lagrange expression where the time variable is Ti. There's also a second one, which in this case seems to say that Li does not depend on Qt1. But this is, of course, not what defines the functions Li. It's what's supposed to characterize the solution Q. So this, again, gives an equation, a differential equation for Q rather than a condition on Li. And in this case, it's just that for I different than 1, the partial derivative for Li with respect to Qt1 is 0. We'll see in general what this one represents is really another Euler-Lagrange equation, but the base variable is Qt1 instead of Q. And since in this story there are no second derivatives, there is no second term here. The third one here is a truly new one that you would never see if you take the Lagrangians individually, because in a sense it's a compatibility condition, something involving Li equal to something involving Lj. You can think of this as saying that the momenta defined by the different Li and Lj should be the same thing. And before I tell you how exactly to obtain these equations, let's look at a simple example. I take the Kepler problem, so potential is 1 over the distance, the usual kinetic energy of being velocity square. Kepler problem is integrable. In fact, it's super integrable. But to keep things very simple, I'm just going to take here one additional flow. So I take the actual physical flow and one rotation around a fixed unit vector v. And at first sight, I mean, it's not clear why this particular L2 should be a rotation. Though I will say that it's quite a general form. If you have an L1 that is of the usual Newtonian form with this kinetic energy, then the other L's are usually of the form T1 derivative times Ti derivative minus the corresponding Hamiltonian. But whether or not you know this general connection to the Hamiltonian, if we just take these two Lagrangians at face value, what comes out the multi-time Euler-Lagrange equations? Well, first we have the usual Euler-Lagrange equations for the two Lagrangians. So we get the usual Newton's equation for the inverse squared force for Kepler's motion in a gravitational potential. If we take the usual Euler-Lagrange equation of L2, we get this equation, which might not be immediately clear what it represents. But if we look at the next equation, what I in the previous slide called the Euler-Lagrange equation with respect to Qt1, then we get an evolutionary equation for T2 that is clearly just a rotation around the fixed vector v. And if we then look back at the previous line, well, this is just the T1 derivative of the equation below it. So this second type of equation actually now gives us the rotational symmetry, its flow in a more explicit form than the traditional Euler-Lagrange equation of L2 would do. And then the final equation, maybe it's a little disappointing here, it is entirely trivial. Qt1 equals Qt1. So this was the really new equation, the compatibility condition between an L1 and L2, and it's trivially satisfied here. But that does not mean it's meaningless. What that means is that we've chosen our Lagrangians in a way that they are compatible with each other, in a way that they induce the same momentum. So the fact that this last one is trivial just means that we have chosen our Lagrangian coefficients in a compatible way. So that as a little example of how to use these equations to capture a system together with its symmetries in one variational principle. But I think I also owe you a little bit of an explanation why the equations I stated are the Euler-Lagrange equations of this variational principle. The formulation of the variational principle says that for every choice of curve gamma in multi-time, this action must be critical. But in fact, it's sufficient to look at a much smaller class of curves, which I call stepped curves. So they're piecewise straight, and the straight pieces are in coordinate directions. So in 2D, it becomes a staircase like this. And if you make the staircase finer and finer, you can approximate any given smooth curve as well as you want, and in such a way that the difference in their action integrals will be as small as you want. So by an approximation argument like that, you can show that if the action is critical of all stepped curves, it will be critical on all smooth curves as well. So we can restrict ourselves to these staircase curves, these step curves. And then the next simplification is the idea that variations can always take locally. If you have a variation that has quite a large support, you can always use a partition of unity to write this as a sum of partitions, a sum of variations that are supported on smaller neighborhoods. And so we can always look at a small section of such a staircase, and that should be sufficient. So it is sufficient to look at one single corner like this. And I still have the same assumption here on which derivatives occur in Lagrangians, which is not essential at all for the argument. The argument works for arbitrary dependence on derivatives, but for the sake of writing down compact formulas, I'm sticking to this more restrictive dependence. So once we've restricted to a single corner, once we've convinced ourselves that it's sufficient to look at one corner like that, then, well, we can look at each straight piece of the corner separately and do the usual calculus of variation. So let's look at the horizontal piece here. The integral, the action will be Li dti. And if we take a variation of that, we get, in this case, 3 terms, because we've assumed that the Li depends on Q, on Qt1, and on Qti, so we get the corresponding 3 variations. And then we do the usual thing in the calculus of variations. We integrate by parts to try and get rid of these derivatives on the variation. We can do this for ti here, because we are integrating with respect to ti, but we can't do it with respect to t1, because that's not what our integral is. So if we do this integration by parts, we get here the usual Euler-Lagrange expression with respect to ti times the variation of q, but we're also left with this variation of qt1 that we can't integrate by parts. And the next difference compared to the traditional calculus of variations is that we cannot now ignore the boundary term. The boundary of this little straight piece we were looking at is this point C, is the point of the corner. But it's the end of the straight piece, but it's still in the middle of the curve as a whole, so we cannot impose any boundaries conditions there. We cannot assume that the variation vanishes. So instead, we need to keep the boundary term and also keep the boundary term that will come from the vertical piece and make sure that the two of them cancel each other out. And that is where this multi-time Euler-Lagrange equation comes from. So from the dq coefficient, we get the first type, the traditional Euler-Lagrange equation. The qt1 coefficient here can be regarded as independent of delta q. So its coefficient also needs to be 0. That's the second type of Euler-Lagrange equation. And then from matching the two boundary contributions of the two straight pieces, you get this third type, this compatibility condition, as I like to think of it. So that's in a nutshell how these strange equations come from the Fleury-Lagrangian variational principle. Now, so far I've only been talking about one forms, and I've only been talking about the continuous setting. The discrete setting is also a big part of Lagrangian multiple form theory, but I won't talk about that today. So Lagrangian one-forms, they describe a system of ODEs, so one independent variable each, that commute, so in the sense of being Liouville integrable, but the main idea is that you have a number of commuting flows. That the number you have is equal to the degrees of freedom is actually not that essential to the setup of the theory. So that's what you get out of one forms. Is that two forms, then your action will be over two-dimensional surfaces. So you're generalizing systems, so you're generalizing variational principles that are not defined on a line, but on a plane. So two-dimensional PDEs, often 1 + 1 dimension, one time, one space, like the KdV equation and its hierarchy is a very famous example of this sort. And again, you can do this continuous. You can do it semi-discrete, for example, in a total lattice, where you think of an infinite number of particles in this case, and the particle spacing is your discrete variable, and your continuous time is your continuous variable. And you can do it in a fully discrete setting, which is actually where the whole theory of Lagrangian multiforms started, in the context of integrable partial difference equations of the Abler-Bobrenko-Zuris list. So there is a classification of integrable difference equation on a square stencil in a Z2 lattice. And similarly, you can write down Lagrangian 3 forms for three-dimensional PDEs like Kp. And for the past 15 years or so, this picture was the full understanding. But with our recent work, what I like to argue is that, well, in many cases, it's a good picture, but it's also a bit too rigid. And I will show you examples of Lagrangian 2 forms that actually describe systems of PDEs in 3 dimensions, of 3 independent variables. But before I get to those examples, I will give a little bit more detail about Lagrangian 2 forms. And you'll see the ideas are almost exactly the same as when I introduced 1 forms. Doing exact calculations becomes a bit more cumbersome because the expressions tend to be quite long, but the ideas are exactly the same. So now the central object is a 2 form, Lij dti ttj, and again it lives in this space I think of as multi-time. In many 2 form examples, the interpretation of time is not very strict. So it could be that one of the t variables is actually space. It could be that there is no obvious interpretation of time at all. But for the sake of choosing a notation, I just stick with denoting these independent variables by t for now. And then the pluri-Lagrangian principle says that, well, we have a 2 form, we can integrate it over surfaces. So if the action I define like this, the integral of this 2 form over a certain surface is critical with respect to variations of the field U, no matter which surface I choose, then I say this U satisfies the pluri-Lagrangian principle. So the U here is what previously was the Q, because Q is quite common in mechanics. U is much more common in field theory. That's why I switched the notation here. But the role in the theory is exactly the same. And again, to get to Lagrangian multiform, in addition to the pluri-Lagrangian principle, we require that on solutions, the exterior derivative of this 2 form is 0. So if we take deformations of the surface, that doesn't change the action either. And how you get to multiform or Lagrange equations is again by the same kind of argument. You do an approximation by stepped surfaces. You look at them locally, so look at a single corner of a cube, essentially. And then now we have an additional type of equation. An additional type of equation that involves 3 of the coefficients. So you can think of these equations 1, 2, and 3 as coming from the planar bits of the surface, 2 as the contribution where the two edges meet, and there's two boundary conditions to match. And then type 3 comes from the point where 3 surfaces meet, so there's 3 different boundary conditions to match here. And the equations, as I've written them down here on the left, so my delta are variational derivatives, or generalized Euler-Lagrange expression, and I write indices ij to indicate that the additional derivatives in this expression are with respect to ti and tj, because there's many more directions in this multi-time, but only these ij play a role in the variational derivative. And if we assume that the coefficients only depend on second derivatives, and that in Lij the derivatives are only with respect to ti and tj, then this list here on the left is complete. If we allow general dependence, it becomes notationally very heavy, because you need to allow for arbitrary derivatives, which are in this multi-index capital I here. But the main point I want to get across here is that you still have the 3 types of equations, no matter what dependence on derivatives you have. One equation involving one coefficient, that's kind of just the usual Euler-Lagrange equation. Then one equation involving 2 coefficients, which you can think of as coming from where edges meet, and then one relating 3 of the Lagrangian coefficients. And I've mentioned the exterior derivatives several times, but it's worth looking at it even more closely. Because if in the pre-Lagrangian principle, we say, well, the integral over arbitrary surfaces must be critical. But if we just look for the time being at closed surfaces, so surfaces gamma that we can write as the boundary of some volume B, well, then this action integral can also be written like that by Stokes' theorem. And so taking variations of this action is actually taking variations of dl. And since we can take this volume B to be as small as we want, or completely arbitrary, the only way that this right-hand integral will be 0 for all variations of all volumes B, the only way that can happen is that pointwise variations of dl are 0. Or, well, all partial derivatives of the coefficients of dl should be 0. So this is an alternative way to get from the variational principle to explicit equations. One way I showed you is through these multiform Euler-Lagrange equations from the stepped surface approach. The other way is just to take pointwise variations of the exterior derivative. And in many cases, this is also quite explicit, because you can usually find a factorization of the coefficients of this exterior derivative. And, well, how you do that is a different question, but suppose you know that the exterior derivative, which is a 3 form, takes this form. So each coefficient is of the form a times b. Then you think of the system of equations a equals 0 and b equals 0. Then this condition of pointwise variation of dl is satisfied. If you take a variation or a partial derivative of this dl, the variation by the product rule will either act on A or on B, but not at the same time. So if you're looking on the system A equals 0 and B equals 0, then variation of dl will be 0, so the variational principle will be satisfied. So this gives you a completely different way of looking at the equations characterizing the variational principle. And sometimes this equivalence is obvious between these equations from the double zero property and the multiform Euler-Lagrange equations, but sometimes this equivalence turns out to be quite non-trivial. And most of the rest of the talk is examples of this. But the first one is still a very general phenomenon. So quite early on in the the story of Lagrangian multiforms, it was realized that there is a very close relationship to variational symmetries and Noether-Stima. And in particular, you can use variational symmetries as a guidance to construct Lagrangian multiforms, because dl equal to 0 is essentially your conservation law that belongs to your variational symmetry. On this slide, I try to make this a little bit more algorithmical. It's mostly based on this paper of the Leeds group from 5 years ago. So suppose you know one Lagrangian. So you have an equation, you know it's Lagrangian in the traditional sense, and let's call that one L12. And we'll try to construct L13, L23 that together build a multiform. And what we'll use is the Lagrangian we'll know, and we also know that it has a variational symmetry, which we write as the T3 derivative equal to, well, whatever the characteristic of the variational symmetry is. And so variational symmetry means that the T3 flow leaves the action invariant. You can write this in a couple of ways. So if you take the Fréchet derivative in the direction of this Q of your Lagrangian, then the action of that should be 0. If you integrate that by parts, you can write it as the variational derivative of L times the right-hand side of the flow. It should be 0. I use the integral here with 0 boundary conditions, or as just a formal equivalence modulo x derivative. So I do integration by parts without worrying about boundary conditions. So in that setting, what it means for an integral to be 0 is the integrand must be a divergence. So the fact that T3 derivative equals Q is a variational symmetry implies that this product here must be a divergence. Now, no matter what T3 is, we can always do this idea of integrating by parts. The change in the action will always be of this form, variational derivative times how the U changes. So in general, even if it's not a variational symmetry, we have that these expressions in the integral are equal up to a total derivative. It's just integration by parts. But if you combine these two expressions, these two local expressions on the right, then you can rearrange them to get this here. So the mn and mn with hats have been combined now into this L23 and L13. So everything that has a total time derivative is combined here in the terms of the left-hand side. And the right-hand side is made up of these terms involving L12, its variational derivative, so this one and this one. And what we get on the right-hand side, so what we get on the left-hand side is a total divergence, or in the language of two forms, it's a coefficient of the exterior derivative of this two form. And on the right-hand side, we see this factorization, what I called a double zero structure. Which means, by the theory of the previous slide, that if we look at the system A equals 0 and B equals 0, which in this case means A equals 0 means the Euler-Lagrange equation, the traditional Euler-Lagrange equation of L12 is 0. So the Lagrangian that we started with, it's Euler-Lagrange equation. And B equals 0 is just the variational symmetry we combined this with. So from this construction, we know that this two form here, its multiform Euler-Lagrange equations will be satisfied on the original Euler-Lagrange equation combined with the variational symmetry. So by construction, it captures the original Lagrangian and its variational symmetry in one principle. And I'll do this, I'll show this explicitly for one of the simplest examples, that of the KdV equation. Actually, it's the potential KdV equation. So the actual KdV would be in in a different variable. Let's see if I can get this the right way around. I think if you take v to be the u1 derivative, then the corresponding equation in v will be the usual KdV equation. And this potential KdV equation, so this is the equation, has a very well-known Lagrangian. It's easy to verify that this L12 here gives, well, not exactly this equation, but the differentiated version of this equation as its traditional Euler-Lagrange equation. And notice that now all my derivatives are, again, all my subscripts are again derivatives. So u1 means the t1 derivatives, u111 means the third t1 derivative, u2 is the t2 derivative, and so on. And we all know that KdV is part of a hierarchy. I'm just going to take the next flow in the hierarchy and stop at that. So the next flow can be written like this. So t3 derivative equal to this fifth order expression. And that is a variational symmetry of this Lagrangian I just wrote down. So with this general construction from the previous slide, we can, based on these 2 points of data, write down additional Lagrangians L13 and L23 such that the exterior derivative of the corresponding 2 form has this factorized structure. And then from the double zero property, the theory says that the multi-time Euler-Lagrange equations should follow from this one, which is the Euler-Lagrange equation of L12, and the evolutionary equation, that's the variational symmetry. And indeed, this is the case. So what comes out of the construction are these 3 Lagrangians. So L12 is exactly the one we started from. L13 has quite a similar structure. Again, almost everything in here is just T1 derivatives, except in the first term for L12, it's UT1 times UT2. For L13, it's UT1 times UT3. So just like in the one form case, these L12, L23, you can think of as kinetic term minus potential term, or something minus the corresponding Hamiltonian. The L23 is a lot more complicated, and so you have both the 2 derivative, the 3 derivative, as well as a lot of T1 derivatives, all mixed in not a very obvious way, I would say. The point is not to stare at this expression and make sense of it. The point is to compute the multiform Euler-Lagrange equations and check that what we want comes out. So the first type of equation is the usual Euler-Lagrange equation for each of the L's. The one for L23 is quite complicated, but please just believe me that it is a consequence of the other ones I have on the slide. For L12, we get the potential KdV equation, but in its differentiated form, just like it was before we started thinking about the multiform. Now, if you take the usual Euler-Lagrange expression for L13, we get a similar equation, a similar version of the next member of the hierarchy. So we get the fifth order KdV equation, but in its differentiated form. So it's a T1 derivative on both sides. But actually, from the next type of Euler-Lagrange equation, one that involves 2 of the coefficients, this one gives you the equation of the variational symmetry in its evolutionary form. So that's consistent with what the theory says about double zeros. When you have a factorization like this, exactly these 2 equations should be equivalent to the system of multiform Euler-Lagrange equations. And indeed, we've recovered these 2 equations and some other equations that are differential consequences, but that's fine. And with this particular 2 form, if you look at other equations, for example, the other 2 ways of matching 2 of the coefficients, you get trivial equations. And there's a few others that I haven't written on the slide, but either they are trivial as well, or also differential consequences of the ones we've already found. So this is an example of how to construct a Lagrangian two-form from this general idea of this general construction from variational symmetries. But this is not actually the two-form you usually find in the literature for KdV, because you can write down a slightly stronger one. So if we go back to the double zero structure, so the form we constructed, by construction of our Lij, we had this factorization of the exterior derivative. And the first one here, the Euler-Lagrange equation of L12, it is a T1 derivative of something. So we could, again, essentially integrate by parts and move this T1 derivative here to the second term by changing what goes into the L23, which is under the T derivative on the left-hand side. And I want to do this, but only with half of this right-hand side. So I split this right-hand side into two halves. One half I leave exactly as it was, and on the other half I do this integration by parts, so that now the second term is under the T1 derivative. And again, this is, I still call this a double zero factorization, even though now it's not of the form A times B, it's a linear combination of two terms of that form. But if you recall, the reason why this factorization is useful, the reason why this double zero property gives us the equation, is that in the variational principle, we're taking variations of this delta L. So if we have a form like this, it's fine too. The variation will always act either on A or on B, but not both at the same time. So if we have a sum of terms like this, on the system of all A is equal to 0 and all B is equal to 0, we'll still find that this variation will be 0. So this is also a perfectly good double zero expansion. But now the equations we need to make each term 0 are the evolutionary version of both of the equations. So u3 equals q, ut equal third derivative plus the square term. So by this little trickery on the multiform, we actually change the multi-time Euler-Lagrange equations. And we can, well, this is what the theory about the double zero property says, but we can easily verify this as well. I haven't put the explicit expression of the new L23 on the slide, but again, it's quite a big one, so it wouldn't be very enlightening. The structure of the multiform Euler-Lagrange equations now is the same thing as before happens with the traditional Euler-Lagrange equations. We haven't actually changed either of these coefficients, so that's no surprise. We still get the evolutionary form of the variational derivative from one of these compatibility conditions, one of these Euler-Lagrange equations involving two terms. But then previously the other two of this form were trivial. Now only one of these is trivial, and the third one gives us the evolutionary form of the KdV equation. So just like in my introduction with the Kepler problem, one of the new equations gave the rotational symmetry in its evolutionary form. Here with KdV, if we choose the two-form smart, we get not just the variational symmetry in its evolutionary form, but also the potential KdV itself, something that would never be possible if you look at the traditional variational principle just involving a single scalar Lagrange. And again, every equation that I'm not writing down is either trivial or a consequence of these two evolutionary equations. Right. Let me move on now to what is actually our recent work with Xenia Ferapontov. And I'll be able to go a little bit quicker now we've established the background. So far, in the previous section, what I did is starting from a Lagrangian and a known variational symmetry, I construct a Lagrangian multiform, and its exterior derivative factorizes like this. So we can use the double zero property. And in other words, we have a conservation law, because on the equation A equals 0, or B equals 0 for that matter, but on the equation, we have this divergence equal to 0, so we have conservation law, which is essentially just a reproduction of Newton's theorem. But what if we don't know this Lagrangian to begin with? What if we don't even know if this equation A equals 0 has a Lagrangian? Well, if we just have something of the form A times B equals a divergence without any mention of Lagrangians or variational derivatives. Well, we can still try to use the coefficients of this divergence as coefficients of our two form and see what happens. And it turns out in many cases that is a sensible system, a system of equations that are in involution, that commute somehow. And the first set of examples we have for this is based on something called the Mikhailov equation, which is PDE in 3 variables. So again, subscripts here denote derivatives. So derivatives up to second order with respect to derivatives. Now they're called x1, x2, x3, because I think there is no sensible interpretation of time for any of these. And it is known that this equation possesses a large number of conservation laws of first and second order, maybe of higher order as well. That won't be relevant. And so whenever we have a conservation law, so for me in this conservation law means a divergence that is 0 on the equation. So functions f, g, and h, so that if you take the corresponding derivatives, you get something that is the equation, the Mikhailov equation, times something else. And I should really be writing f is L23, g is L31, and so on. But to keep the number of subscripts in check, I'll stick with FGH here. But those are the coefficients of our Lagrangian multiform, or are supposed to be. So from looking up the conservation laws of this equation, we can find a lot of expressions like this. And it turns out that in all of these cases, the equation B equals 0 is actually compatible, or involutive, as we tend to say, with the Mikhailov equation. So this system makes sense as commuting flows, even if there aren't really flows. And because we have this conservation law, we have exterior derivative equals double zero of these equations. So by construction, these f, g, and h give us a Lagrangian multiform for that system. So we have a Lagrangian 2 form here, because that's, well, by construction, it's a 2 form. But what it describes is a system consisting of this 3-dimensional PDE and something else. In the first example we have here, the something else is kind of this completely trivial ODE, but in a formal sense, these two equations are still compatible, so it's a valid example. So this example would be a Lagrangian 2 form describing a system that is part ODE, part 3D PDE, whereas traditionally in multiforms, as in the example with KDV, a 2 form would just describe a 2D PDE. And we can change this example a little bit by adding some first order terms, and then the factorization becomes a bit more interesting. Again, you have this Mikhailov equation as one of your factors. In the previous example, the second factor was just the third T1 derivative. Now there are some more terms, and look at this, together they again give us the potential KdV. So with this expressions for FGH, which are the coefficients of our Lagrangian 2 form, we get a Lagrangian multiform that describes exactly this system of PDEs, one of which is in 3 variables, the other one is in 2 variables. variables. And again, these PDEs are involutive. They are compatible with each other, which we don't really understand why that happens. Another conservation law of the Mikhailov equation just comes from a noise classification. This gives the same structure. One coefficient is Mikhailov equation. One is now a very big PDE, but still a PDE in two variables, the one variable and the three variable. And it turns out to be a known equation as well. Gurevich-Zidin is its name. We also have examples. So there's a few more examples for the Mikhailov equation. They only get more complicated. I don't think it makes sense to show any of them. The point I want to make is that here, by just starting from the observation that this Mikhailov equation, this 3D PDE, has a conservation law, and by noting that the conservation law as a flow is commutative with the Mikhailov equation itself, this means that we can write down a multiform for this involutive system exactly based on this double zero property, because whenever the exterior derivative here factorizes a times b, we know that these two are exactly equivalent to the system of Euler-Lagrange equations. We can even do examples where A and B are both three-dimensional PDEs. And this is actually, in a sense, a very old example. You can consider it as a degeneration of an example of a two-form that was in the very first paper that introduced some of the ideas of Lagrangian multiforms. So we take this fairly simple expression as the coefficient on the two-form, and it's perfectly symmetric. So the only thing that changes are which derivatives enters. They always match the coefficient we're at and the prefactor where the c's are constants. And if you take this two-form, compute its exterior derivative, you can, with a bit of work, but by elementary calculations, you can verify that the coefficients of its exterior derivative, again, factorize as a times b, where a and b are these two things here. So we know by construction, by the double zero property, that the system of Euler-Lagrange equations for this Lagrangian two-form should be equivalent to the system of a equals 0 and b equals 0. And both of these equations are known in some sense. A equals 0 is probably the best known. It's something called the Vermeeren-Webb equation. Or if you think of the hierarchy for all possible ijk's, it's the Vermeeren-Webb hierarchy. And that one's related to Einstein-Weil geometry. B also has a geometric interpretation, but one that seems completely disconnected to the geometric interpretation of A. B equals 0 characterizes a certain class of metrics. So diagonal metrics of potential form with another restriction on its curvature. Not quite enough to make it flat, but still it has a geometric interpretation. So this is a puzzling side note as well, that we have this multiform relates two equations with both differential geometric interpretations, but we have no idea how to relate the differential geometries. And so I said that by construction, because we have this factorization, A and B equals 0 should be the system of Euler-Lagrange equations. And if you look at them, the system of Euler-Lagrange equation, we get these three equations. And the third one, it is exactly the equation A equals 0. The second one is quite hard to say much about on site. For the first one, I want to point out that this is a two-dimensional PDE. There's only I and j derivatives here, not a k derivative. And by the theory of multiforms, these two systems are equivalent. But if you want to do this by hand, for example, take A equals 0, B equals 0, and eliminate the k derivative from that, that's an extremely non-trivial task by hand. So in an example like this, the Lagrangian two-form in a sense, is a tool to take these two three-dimensional PDEs and eliminate one of their variables. So depending on which system of equations you look at, you can either say that this 2 form describes a system of two 3D PDEs, or you can say it describes a system consisting of a 2D PDE and 3D PDEs. But in either case, we've again moved on from this idea that a 2 form should describe 2D PDEs only. So the general recipe seems to be that suppose we know an integrable PDE equal to 0. And we know a conservation law in the sense that we know a divergence that is 0 on this equation. So a divergence that can be written as A times B. Then in all non-trivial examples we've looked at, the combined system of A equal to 0, B equal to 0 is an involution, is compatible with each other. So it is meaningful to consider them as a system. And then by construction, through the double zero property of Lagrangian multiforms, and the multiform with these coefficients FGA is exactly describing the system of equations A equals 0, B equals 0 through the variational principle. But this is an observation based on examples. This is not a theorem, especially the part that A and B are in involution. We don't know why this seems to happen, and we don't know under which conditions this could hold in general. So that's a big open question in this story to be resolved, I think. Now, I realize I'm running low on time, so I will, for the final part, skip over most of the calculations and try to give you a sense of the ideas. So this is another example from our recent paper with Chenya Ferapontov. And the idea there is to look at hydrodynamic reductions of some famous systems. So hydrodynamic reductions start from some quasi-linear PDEs of any dimension, really. And the idea is to decouple them into an arbitrary number of 1 + 1 dimensional systems. In these new variables R that have specific relations to each other. And if this works for arbitrarily many, so an arbitrary number of R, then that's an indication that the system 1 you started from is integrable. And we've looked at this in particular for something called the second heavenly equation from Podlansky's work. So first of all, this usual form of it is not quasi-linear. So in order to apply a hydrodynamic reduction to that, we need to rewrite it in quasi-linear form. And the way to do that is so simple it almost feels trivial. You just take 4 of the 5 variables occurring in here, 4 of the 5 derivatives, and make them their own variable. Then the 5th variable is an algebraic function of those other 4. And so that's just rewriting the equation in an algebraic way. But obviously, cross-differentiating these relations gives a set of compatibility conditions. Those are the ones written on the bottom of the slide. And these essentially carry the same information as a heavenly equation, but now they are in a suitable quasi-linear form. So after rewriting it like this, so going from the variable theta to u, v, w, and p, we use this idea of hydrodynamic reductions, which means writing u, v, w, and p in terms of this arbitrary number of independent variables r, but the r's should have specific relations between them. So that's just very quickly the idea of hydrodynamic reduction. And then from both these relations between the r's and the specific form of the equation, quasi-linear equation we're working with, we get a whole number of equations that involves both the u, p, v, and w, the variables from the quasi-linear equation, and the Greek letters, the lambda, mu, and well, eta has been substituted here with lambda, mu, eta, from the structure of these independent variables R. So hydrodynamic reduction gets you from this quasi-linear equation to a bunch of equations in this u's, v, p, w, quasi-linear variables, and the new variables relating the new independent variables. Now, this is still a very complicated systems, but there are additional compatibility condition and commutativity conditions that you can use to eliminate several of these variables. And in the end, oh, it's not really the end, but at some point you arrive at a system like this in one of the quasi-linear variables u and two of these Greek variables. And then you see that there's a very similar form between the Greek variables, so you can actually eliminate one of those as well. And then this is a system we looked at a bit closer, because this system, so these systems arising from hydrodynamic reductions are called Gibbons-Tsarev type equations. And this one in particular, where we've reduced it to mu and u variables, that one has a Lagrangian multiform. And again, there are two ways to look at this Lagrangian multiform, either through the multi-time Lagrange equations or through the exterior derivative, where you get, again, a sum of factorized terms. And in this case, there are no surprises, really, because it's easy to see the same equations occurring in both sets. So we don't get a non-trivial equivalence between those two sets of equations. They are quite obviously equivalent. We can also take this reduction procedure one step further and actually eliminate the mu as well from the system. And that leads to equations we've seen before that gets us in the u variable to the Vermeeren-Webb hierarchy with another third order PDE. And these were exactly the PDEs that came out of the earlier multiform. So this is another slightly open question. In this example, when we've reduced the hydrodynamic reduction to a small enough number of variables, we get to a stage where we have multiforms for these equations. How general this is also remains to be seen. So if you start from other equations, then the second half only, and do this hydrodynamic reduction, do you again arrive at things that have a Lagrangian multiform that we're not quite sure about. So let me come to my conclusions. So most of my talk I spent about the theory of Lagrangian multiforms as it has been growing over the past 15 years. So key idea there is Lagrangian multiforms are a variational principle that capture a system of flows as one. So often it is an integrable system together with its symmetries. They all come out of that single variational principle. And what the big appeal of this theory to me is that with a variational principle, it's easy to switch between discrete and continuous. You just change integrals by sums, basically. And this formalism also applies to ODEs and PDEs of many different dimensions. And typically, these PDEs that have been studied this way have been soliton equations like KdV and LS. And what's also already quite well known is that the closure property, so DL equals 0, is related to conservation laws through Noether's theorem. Now, in the final part of my talk, our new work, the new ideas are that Lagrangian two-forms don't necessarily describe two-dimensional PDEs. They can also describe systems of three-dimensional PDEs. And so presumably this is true across the board. Maybe one-forms could describe systems of PDEs as well. And another new idea that we don't fully understand yet is that the closure property of Lagrangian multiform, yes, it's related to conservation laws, but that's still true when there was no Lagrangian structure to begin with. So that is still true if the conservation law does not arise from Newton's theory. And then the final thing in our paper is that we focused on dispersionless examples rather than the soliton equations that have been typically studied through multiforms. So yes, I hope that conveys the idea of what we've been doing a little bit. I would be very happy to answer questions if there are any. And in any case, thank you very much for your attention.
Okay, thank you very much for very wonderful talks.